So, by the end of this lesson, you'll be able to describe fundamentally what creates a magnetic field, describe the magnetic field formed by a current flowing through a wire, draw and interpret vector arrows in 3 dimensions, describe the magnetic field formed by current flowing through loops of wire. So, I know I hit this in the video, but so there's a couple of facts that I'm just going to tell you that you're just going to have to believe me. Okay? First being that if you get a charged particle and you make it move, it will create a magnetic field. Okay? It's just why? We don't know. We just like, hey, look, it does. Like it was actually discovered by a physics teacher. My guess is they just had a bunch of, it was dirty. Like it was not dirty, but like unorganized, unkept, didn't put stuff away, and they're messing with current circuits. And all of a sudden, like, oh, that messed with the compass nearby. Okay, so was not anticipated, but we do know it occurs. So if you could come back here. What I have is you got to be able to see these compasses up here. So come on over. Okay, look to see the direction of the compasses. Okay. In this class, compasses are used as magnetic field indicators. Okay, so right now they're all pointing this way in the direction of the Earth's magnetic field. Okay. Now, when I turn on the current, notice the pattern, observe the pattern that the compasses are now making. Once you see them, back up so that other people can see. If you want to look at this, I don't know if you want to, yeah. Okay. What pattern are they making? Circle. Okay. May I show you, introduce you to kind of like secret handshake of physics people called the right hand rule. Everybody get your right hand out. Okay. And what we're going to do is we're going to take a pencil or a pen or something, and we're going to pretend like that's our wire. And we're going to put our fingers in the direction of the way the compasses are pointing. Okay. And that shows us the direction of the magnetic field. Should match. They're like, hey, what's up? Okay, good with that. But you can do, like, people have taken physics, other students, you'd be like, hey, dude, no way, man, you got the right hand rule. Okay, what would happen if I switched the direction of the current? Hypothesize. Show me, and then see if that matches what you thought. Once you verified that, go ahead and have a seat. No, I will. Yeah. I used to eat it when I was little, like the little okay, so pouches. If you could see magnetic fields, this is what you would see around a long straight wire. Concentric circles. Going all along, so it'd be like a whole column of magnetic field, getting weaker as you go away from it. You with that? All right, give that one a shot. Tell your neighbor. Correct answer is A. Take your pencil or pen, grab it with your thumb going down. Okay? And your fingers are going around in this pattern. Everybody good with that? Yeah, oh yeah, it's a fun day on test day. All right. Now, physicists usually aren't good artists. And so instead of drawing things like that, they do X's and X's, or dots and X's. This is from the pre-quiz. Tell your neighbor. Okay. So we're all about arrows in physics, right? Vectors. Okay. I'm going to look at a Robin Hood arrow. Okay. When you see the dot, that is the tip of the arrow, the arrowhead coming at you, you better duck. You're like, whoa. Okay. We say that is out of the page. Okay. Or out of the board. Okay. The circle with the X's are the tail feathers as the arrow flies away from you. But we say into the board or into the page. Okay. Correct answer is A. So the thumb's going down on the right hand side. Your fingertips are pointing out of the page. On the left hand side, your fingertips are going into the page. Do you see how this matches this? Communicates the same idea. Okay? So we're thinking three-dimensionally here. Tell your neighbor. Right.
That's so real.
Okay. Correct answer is fancy fox. It's got to be an animal. It's fancy fiddles. Fish, fiddles, foxes. Fantastic. All right. So you grab your pen or pencil with your thumb going to the left at point P. It's coming out of the page at you. And make sure if you see anybody using their left hand, smack them. It's worth it. They need to learn. Okay. Now here's another way to visualize this. If this is like, okay, let's say you had a tennis ball on a string. And you're spinning it around this way. And you let go of the tennis ball at point P. Which way would the tennis ball fly? So this is doing this. The tennis ball is going around like this. Which way would it go if you let go at point P? Out of the page at you, tangent to the circular path. Good with that? Okay. Buddy up. One person be the right hand rule, the other, sorry, nope. One person be the left wire, the other person be the right wire.
So what is the EEH? Like, what is the direction?
Up.
Yeah,
right.
What purpose is it served to be?
You got a lot of options.
Oh, their answers?
Yeah. Yeah.
I thought you said.
Yeah. Correct answer is A. Both. So from the left-hand wire, it's creating a magnetic field going. Oops. Going into the page. Don't think clockwise or counterclockwise. Okay? Going into the page at point P. This one, creating a thumb going down, magnetic field going into the page. Both are going into the page. Okay with that? Okay, now what I'm going to do for this next slide is I'm going to turn off the current in this wire. Tell your neighbor what you think and why you think it. Correct answer is
Beautiful babies.
I agree with beautiful babies. Okay, let's give some numbers here. Let's say there's 5 going in from that wire and 5 going in. That wire, the net field would be 10. You take one of those away, and it's now 5. Good? Okay. Flip in the direction of current. Buddy up.
Person's going in.
So we're looking at right, but you gotta make sure like you right hand, gotta make sure you're that here. So right on the so they're but like if you put them on opposite, like say when you put them here, this so G. So I think it's just on the other end. We were thinking like overall there's like the same direction, but it's like 8%. Wait, what are we doing with point B?
Correct answer is
Crazy cat.
Wait. I need you to explain this one.
Yep. Okay. Correct answer is Crazy Cats. This one again is creating a magnetic field going into the page. Okay. Here's your pencil, your wire. Stick your thumb in the direction of current. At point P, going into the page. Spinning around. The magnetic field's going around like this. Okay. Everybody good with that? Into the page from the left wire. For the right wire, you're grabbing the wire with your thumb going up as well. At point P, your fingers are going out of the page. So they're going in opposite directions, so they cancel each other out. Good with that? Change the location of point P. Bless you. Talk to your neighbor. Correct answer is. Got 1 vote for B.
Beautiful babies.
2 votes for B. Okay. So here, this one creates a magnetic field coming out of the page. Right? This one creates magnetic field going into the page. Why is the net magnetic field out of the page? This one's closer to point P. Therefore, its magnetic field is stronger than the one created by this current. Okay with that? So overall, B. Yep. Bouncing babies. Tell your neighbor. Tell them why you think so.
Oh, I can put there.
Correct answer is? Correct answer is A. Because if making up numbers here, let's say this was 5 and this was 2, the net magnetic field would be 3. But if you kill the current in that one, then the net magnetic field is 5. Good? Mega. What's the unit? Tesla. We'll get there. Pre-quiz tonight. Okay. On this question, my recommendation would be to look at each side. Tell your neighbor. Correct answer is? Correct answer is B. Bountiful buffaloes. Left side. Thumb goes up, in. Top. Thumb goes to left, or sorry, right, in. Right side, thumb goes down, in. Bottom, thumb goes left, in. All sides point in. Tell your neighbor. Tell them why you think so. What do you say? Correct answer is A. So this is a crazy thing. It's A because each side is adding and contributing to the magnetic field versus the straight wire. There's just one side, one making a magnetic field. Here you got this, 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 and this. Now, rarely do you see a square wire, a square loop. Usually you'll see a circle. But here's the crazy thing. All you need to do is put wire that has current flowing through it into a loop, and all of a sudden you've got a really strong magnetic field. That's a really simple trick for creating a strong magnetic field. Okay, good with that? So to evaluate, so this would be an idealistic loop of wire. Okay. What I want to know is what's the direction of the magnetic field inside the loop of wire. That's what we're going to be using and employing. That's what I care about. Okay, so to figure out the direction of the magnetic field inside the loop of wire, here's what you're going to do. You first look at the part of the wire that's closest to you. So you got to think of this three-dimensionally. This part of the wire is far away. This part of the wire is close. Everybody okay with that? Okay, you're going to grab that part of the wire, the closest part of the loop. Okay, but put your thumb in the direction of current. Okay, so here's your pencil. I'm going to grab this with my thumb going to the right. The magnetic field inside the loop is behind this, because this is part of the wire that's closest to you, part of the loop that's closest to you. The magnetic field is going up. So everybody see that? How that's, you're grabbing this part of the wire, it's going up. Okay. So if we could see magnetic fields, this would be a plane, one of the planes. But the reality is it's actually three-dimensional. So it gets really strong inside the middle there. Good with that? So what this picture is a loop of wire with current flowing through it, creating this magnetic field. I want to know, is the current going to the right or to the left? This picture is just a side view of that. Tell your neighbor. Correct answer is beautiful babies. Okay. You're going to grab. So the magnetic field is going down. Okay. Behind this. This is the part of the wire that we're focusing on. It's going down. You can't grab the wire like this. You can grab the wire like this. So the thumb is going to the left. Everybody good with that? Okay. All right. Join me back here, please.
She's not fast. I tried.
All right. Now, what I have is a single loop of wire. Sorry, a single wire wrapped a whole bunch of times. Okay. Now, got a compass that's pointing some way. Okay. Now, when I turn on the current, okay, turn it off, turn it on. Okay. So what I want to know is what is the direction of the current going through this wire? The magnetic field is going which way? What's the direction of the current going through this wire? Is it going this way or is it going that way? Probably need your right hand to figure it out. Just a suggestion. So you're going to stick your fingers in the direction of the magnetic field inside here. So they're either going this way. I'm going to grab this. I can't grab. This is getting awkward. I can't grab the wire this way. Nope, that's not the way. Can't grab the wire this way. That makes sense? I have to grab it this way. So the current's going this way through that wire loop. Good with that? So you're looking at it inside the loop. Okay. Now, what I'm going to do is do some iron filing here. And I'm going to sprinkle some iron filings on here. Generous amount. Okay. Now I'm going to turn on the current. Shoot. Turn on the current. The video audience. Okay, for you all now, come check out the pattern it is creating. That's a lot there.
More the merrier.
See the lines?
Mhm.
Okay. Now, check this out. If I take a piece of steel, which has iron in it, and stick it in here,
Whoa. What? Whoa. That's
Okay.
strange.
now, Camden, can you turn off the power? Watch what happens. Watch the wrench when I turn off the power.
What?
If I turn it back on, what did I just create?
A magnet.
An electromagnet. A magnet that I can turn on and off. Okay, now, if you notice, it is still slightly magnetized. Okay, that's because I caused some of those domains, those magnetic crystals, to align themselves in this magnetic field. It's strong enough to make those flip. Okay, now if I okay, now watch this. Not much. It's still there's still a little, but not much. If I drop it again, ooh, put a dent in my floor. Still a little bit. I have to really whack it.
Just chuck it out the window.
That's nothing. Nothing. Okay? Good with that? So, this is how you make magnets. So, this was the magnetizer that I was here when I got here. It's like World War II technology here. But so if I stick the magnets in here like that, and then turn, so this is one wire wrapped a whole bunch of times in 2 loops. These are solenoids. These are now been magnetized.
What? So it's basically a magnet maker?
It is a magnet maker. Okay. Now, so check this out. I'm going to stick it in incorrectly. So I've got south and south.
What?
South and south now attract. Because I magnetized one of these incorrectly. That makes sense? Like this is really the north, even though it says S.
Oh, it's that. Oh.
Okay. I switched the domains. Made them go the other way. Now if I load this in correctly, I remagnetized it. South and south do not, they repel, but north and south.
What is this?
Okay.
Yeah, what would happen if
I don't know if it'll fit because it has to be a certain. Oh, there it does. So
So
now
what do you think happened to that now? Like what?
it's fine.
It's just the same.
A horseshoe magnet is just a bar magnet
Yeah,
that
it's
got
just like
bent.
bent. Yeah. I thought I got stuck for a second.
So I don't know which one's north or south, but it works. Like one's north, one's south.
Oh, it's like
You could.
affecting the magnet a little bit.
Oh yeah.
Whoa. Crazy.
Okay. Good with that?
Sure.
Have a seat.
Thanks, bro.
Sure.
See, I'm just improving the lab.
Yeah, you are.
Just dude, magnets are so much fun.
All right. All right. Give this one a shot. So this one on this is the positive terminal. This is the negative terminal. This compass is supposed to be inside the loop of wire, just like I showed you on the demo. Talk to your neighbor. Just points in the direction of the magnetic field. The painted part, the red part, points in the direction of the magnetic field. So the current is going out of positive into negative. So I'm focused on this part of the coil, part of the loop that's closest to me. Okay, so I'm going to grab this wire with my thumb going to the right. Inside the coil, so behind this, my fingers are going up. Correct answer is C. Makes sense? I want the magnetic field inside the loop of wire, so behind this. Okay. All right. So if you wrap a bunch of coils around it, you get a solenoid. Creates a really strong magnetic field. So here would be like the plane, like I did with the iron filings, but in reality, it's three-dimensional. So it's really strong. Wait for it. Boom, there it is. Okay. So, and that's why we could make magnets. Okay. I'm going to tell you this one. Outside the magnet, field lines go out of north into south. But inside the magnet, they go from south to north to make full loops. Does that make sense? So the right side is the North Pole. Here's my recommendation. Focus on this part only. The current's going that way. Does that make sense? You're looking at the part of the coil that's closest to you. Tell your neighbor. Correct answer is C. Crazy cats. Here's the wire you're focused on. You put your thumb going up, grab it on the inside, so behind this, inside the loop. Fingers are going to the left. Okay. C was it right on that previous one. Yep.
What type of wire?
Just anything. Mhm. Yep.
I got the idea. My Dylan Park. My drill magnets.
Ready? All right. So I want this side to be north, that side to be south. So field lines go out of north into south outside the magnet. So inside it's going this way, magnetic field. Okay. I'm going to focus on this wire here because it's closest to me rather than this one. That's behind. That's far away. So I want inside, so behind, I want my fingers to go up. I need to grab this wire though. Can't grab it that way. Need to grab it this way. So current's going that way, and the top wire, correct answer is A. Current needs to go this way. You do that. Okay. There you go. Got a pre-quiz due tomorrow.
Real well.